Today I thought I'd talk about one of the matrix algebra examples. It's a little bit easier. One doesn't have to worry about division algebras. And if you remember, there were Gopal and Saiki showed that there were 9 division algebras to worry about, and there are about 6 matrix algebra cases to worry about. And they're 6 of the 40 group pairs, field pairs, C sub I. So this is C sub 11. Okay, so it's nice that L is a cyclotomic field, and it satisfies that degree 4 equation. So it's a degree 4 extension of the rationals, and inside it, it has the square root of 3. So if you like, you can think of L a slightly less elegant way as Q with the square root of 3 and I adjoined. Okay. So we're going to use this form F. So it is chosen for the reasons that we've mentioned before, that you want the correct behavior at the real places. So this particular F has determinant 1. It's got, when R is the positive square root of 3, this is, has got what's called signature 2, 1. And when R is a negative square root of 3, it's definite, has signature 3, 0 or something, whatever it's called. And you form this group here, which is an example of what I was talking about last time. We're using the involution of the second kind iota, like this, and whereas the condition last time was written in terms of iota times an element, iota of the element times an element is 1. These are equivalent, and so so this condition we see here is the same as this condition here. Okay. So as we've mentioned, it doesn't matter which F you choose, provided the signatures work out according to the 2 places. So there are 2 embeddings of K into the reals, mapping R to either plus root 3 or minus root 3. And if you choose the positive square root of 3, you can you get the behavior SU21. So I've actually written down a specific conjugating matrix delta. So for this particular choice of delta, F0, remember, was the matrix and that used to define SU1. And if you do a little calculation, you find this happens. And so a matrix G satisfies the condition that we saw in the previous slide, if and only if its conjugate by delta satisfies the condition necessary to be in U21. And without going into details, that means that there's an isomorphism from G at that completion KV with SU21, which is one of the things you want. And the other thing you want is that if you take the other square root of 3, the negative square root of 3, so this is a different delta, so I've just fiddled with it a little bit, and this time delta star delta without an F0 in the middle is equal to a multiple of F. And so this time the condition in the definition of G holds if and only if this conjugate here satisfies this. And so that's the unitary condition, so being in U3. So this gives you the desired behavior at the other Archimedean place. Okay. So if you remember the formula that I like, that I mentioned last time, all these numbers dkl are known. Alpha is 1 because we're in the matrix algebra case. There's no set T0, or it's empty. And the number dkl is 864. So this formula star simplifies a little bit to this. And there are these factors E prime of PV corresponding, which appear in the volume in Gopal's volume formula. And rather than listing all of them, I'll just mention that if phi splits, then this term divides E prime of PV. And if phi doesn't split, this term divides E prime of PV. So if you have any V's in T, then one of these factors has got to divide 864. And 864 is a pretty big number, but unfortunately, it's only got 2 primes in it, 2 and 3, and it turns out that q squared plus q plus 1 never divides 864, and the only q prime power q that for which q squared minus q plus 1 divides 864 is 2. So in this formula here, there can be at most 1 term. Okay. So this game we play, or Gopal and so on played before, because we know the specific DKL, the possibilities here are extremely limited. Okay. Now, it could be, so it turns out that the prime 2, so Q is K is a field of degree 2 over the rationals. So it could be that 2 has 2 could split, but in fact it ramifies. And to see that, for example, you can observe that 2 times OK is the square of this particular prime ideal. It's a little calculation. So there's only one 2-adic valuation on K, and Q sub V is 2. So that is a candidate for the previous slide. So QV equals 2 is around. I mean, if it didn't split, if it was inert, then Q sub V would be 4, and then even that V would not be possible. But in fact, QV is 2 here. So the possibilities for this T, it's empty, or it contains the one 2-adic valuation on K.
I thought that in this case the E prime factor was 1 when it ramifies.
There's no ramification. So the ramification happens when there's, so the E prime is 1 when there's ramification of the place in L. In L. You see, the ramification, in L.
2 ramifies in.
2 ramifies in K, but there are no V's on K that ramify in L. Okay, so I'm going to look at the case when T is empty, when there's no factor. Okay, so that means the product of those E prime of PVs is just not there, and we simply have this equation. So I drew a picture last time, and this is a specific, this is the same picture from last time in this particular case. Previously there was a 3 to the alpha, it's 3 to the 1 because we're in the matrix algebra case. And we're imagining pi as a fundamental group of a projective plane. We're looking for finite projective planes, fake projective planes, and we know that its pullback in SU21 has to sit like this. Okay. So our method, our goal is to understand this gamma bar, to get a presentation of gamma bar, and then look for subgroups of 864, of index 864 inside there. Okay, so that's our strategy. We want to concretely realize gamma bar and get a presentation for that group. And then we want to go looking for subgroups of index 864, which have the extra properties of being torsion-free and have finite abelianization. Okay. So to cut to the chase, there is we finally show that there is up to conjugation just one torsion-free subgroup of index 864, but its abelianization turns out not to be z squared, and so you do get a smooth ball quotient, but it's not a fake projective plane. It's got the wrong first Betti number. So that's sort of leaving the giving you the climax right at the beginning, which is a bit of a shame, but there you are. All right, so now I want to choose parahorics. So remember in this formula, well, in this diagram, there's a lambda, and this is sort of product, so to speak, a product of parahorics, and we want to choose them. So I started telling you about how this works in the division algebra case, but also in the matrix algebra case. It's a little bit easier. That if you look at the kV points of G at a place where V splits, you get SL 3 kV, and we're going to choose as our parahoric SL3 of OV. Okay, so unfortunately I'm using slightly different notation from Tim. I'm using math frac, and you're using math cal or something for, anyway, I'm using a Gothic German O there, and but I think we can live with that difference. I'm using, also I find it easier to work with the SL rather than the PL, but it's not important either. So, I mean, one has to pay attention, but it's not so important. So now, what happens when V doesn't split is that the group of kV points is a unitary group. This P F sub V is the F that we started with, but just its image in the relevant completion. So one has to be a bit careful about distinguishing those. For example, we saw when we're dealing with the two real places, it depended on which embedding you chose, whether F became definite or wasn't definite.
Those are matrices over L.
Oh yeah, yes indeed, that's a mistake. Yep. So that should be that should be the completion of L with respect to the unique extension of V to L. Sorry. Thank you, Tim. I do remember in this line though that so I call the unique extension V tilde. So we've got a V here, and being a pedant, I give it a different name. Tim called it the same thing. It's got a unique extension. When in the non-split case, there's a unique extension of V to L, which I call V tilde, and this is the valuation ring. Okay. So we make those choices, and we let lambda be the principal arithmetic subgroup where we use PV for these particular choices of PV. Okay. So so there are no type. Tim was talking about type 1 and type 2 conditions here. Everything's type 1. There's no technicality like that. And so we have to understand what it means to be in lambda. So we're dealing with matrices here, and I is already taken, so I'm using alpha and beta as my indices for my matrix elements. And so the A and B are in the field K, and it works out in the isomorphism of the previous slide, for G to be, or for G sub V to be in PV, what you need is that for both extensions of V, the valuation is non-negative. Okay, so So in the split case, there are two places of L above V, and if you work out what it means for V, this should be G sub V. For G sub V to be in PV, what you need is that for both places, the entries have non-negative valuation. In the case when V doesn't split, for GV is in PV if and only if at the one place where you have over V, you get non-negative valuation for every entry. Anyway, analogous to what Tim was saying about how to say that a number is an integer if and only if its denominator doesn't have any 2's and it doesn't have any 3's and it doesn't have any 5's, so on. If an element of L, for it to be an integral element of L, you just need that the valuation at each non-Archimedean place be non-negative. Okay, so to be in lambda means that happens for each of the entries. So, by the way, this is a nice little fact about cyclotomic fields, that the ring of integers is just the, I've forgotten the name for it, but it's just Z of zeta, or Z of zeta if you're from the wrong side of the Atlantic. Okay, so in short then, to be in lambda, you're dealing with elements, 3 by 3 elements, which have entries in Z of zeta, which are unitary with respect to F, and which have determinant 1. That's to be in lambda. So we need to find elements, so this is where I'm trying to get in sync with what Tim's notation was. I need also the elements, the matrices with elements here satisfying this unitary condition but dropping the condition of the determinant being 1. The reason for that is I want to get the normalizer this normalizer inside. So we've described lambda, we also need gamma, the normalizer. So if you drop the condition that the determinant is 1, just the fact that you've got entries which are algebraic integers implies that the absolute value squared of the determinant is 1, and if it's an algebraic integer, that forces it to be one of the 12 powers of zeta. Okay, so there's a finite little group there, and well, here I'm banging on here about how really this lambda embeds in here via conjugation. Okay, so if I take an element G, which has determinant zeta to the j, and if I map that zeta to this, if I put in a fudge factor, this will normalize the image of lambda in here. And it's not hard to see that that's how you get the normalizer. Okay. It's especially easy well, it's known by general results of, algebraic groups, but you also know that the index is 3, so it's just enough to produce one element which is in here but not in here, and which looks like that, and then you're done. Okay. So as Tim mentioned, we haven't been actually finding any elements of these groups concretely, so here's where we start doing that. So I need to look at the geometry just a little bit. So we're going to use the action of U21 on the ball, which is well known to you, I'm sure. This preserves the hyperbolic metric, which satisfies this. I'm sure these things are very familiar things to you. Now, when you have an element in U21, this turns out to be quite a useful fact. The column, the third column, has this property. And when you evaluate, when you look at the action of G on the origin, you find that you get this. And if you plug that into the formula on the previous slide, if you plug that into this formula here, and do a very small calculation, you find that cos squared of the distance from GO to O is just the absolute value squared of the 3-3 entry. Okay. So one of the things, one of the ways of getting elements of this group is to ask for the elements which fix the origin. Okay. So what does it mean to fix the origin? If you're working in U21, just looking at this formula here, you've got to have G13 and G23 being 0, and a little fiddle will show you that also those two are 0. So they're the elements of U21 which fix the origin. Now we're dealing with a slightly different situation where G isn't unitary with respect to F sub 0, where it's unitary with respect to this F. So to get it in U21, I have to conjugate by this matrix I call delta. And so our group still acts on the unit ball, but we have to do this conjugation first. So the definition of the action of G on Z is that it's, in fact, the action of G tilde on Z. So scalar multiples of the identity act trivially, so this finite group here acts trivially, and so one convinces oneself very quickly that from the fact that gamma looks like the ones that satisfying this, to its image. Its image, gamma bar, is isomorphic to this. So this is a group we really need to play with, because then we want to find subgroups of index 864 in there. This delta map is so upper block, has an upper block, and so when you do this conjugation, you don't change the G33. So in fact, the square of the hyperbolic cosine of this distance is still G33 absolute squared, even if we're working in this, even if we're working with G satisfying this. So there's the column 3 condition, as I call it, which applies to elements of U21, has an analog when you're dealing with G's satisfying this. And it's easy to write it down. It's again a condition only involving the third column, elements in the third column. So in order that G fixes the origin, well, from the previous slide gives you this. Okay, so if G fixes the origin, then this is cos squared of 0, so that's 1. So that means the absolute value of G3 has to be 1. And so that means this term on the right is 0, so therefore G13 and therefore G23 are 0. And after a little fiddle, you see that again, G has to be an upper block thing like that. Furthermore, G33 is an element of, it's an algebraic integer whose absolute value squared is 1, so it has to be a power of zeta. So you're dealing with a very simple situation here, and routine calculations show that these matrices here, U and V, are unitary with respect to F. They have the right form with zeros here, here, and here. So they all fix the origin, and you find an element. You find that you have a group of order 288. So there, Tim, here's some elements of the group. 288 of them. So this is an elementary calculation to check that this is a stabilizer. And if you, for example, you can count that there are 288 of them, and you can see that this is a presentation by getting, for example, by getting Magma to write down the abstract group with that presentation and checking that it's got order 288. So it's anyway. So okay. So now here's a 289th element of the group. It's this element B here. It satisfies. It's unitary with respect to F. Its determinant isn't 1, but it's in here though. And our theorem is, well, our preliminary theorem. So remember, the goal was to get a presentation of this. So then we could look for index subgroups, index 864 subgroups. Okay, so we find this presentation. So I want to explain how we get this and how we find B. Where did this B come from? So these, I mentioned down the bottom here, we are working modulo that finite group of scalar matrices. And so when you look at some of these relations here, they're not true in the as matrices. You actually have a multiple of the identity, but as you're working modulo that little finite group, it's fine. Okay, so I had another method, and Tim and I had another method years ago of finding these elements. This is something I noticed more recently. So I want to talk about that method. So getting back to an element of U21, that means this happens, and after a long fiddle, you see that it's the same as this. Okay, I've got the details there, which you probably, your eyes glaze over as you look at, but I can move the star from the left to the right for free. Okay, and it's because F0 is its own, it's square, it's equal to its own inverse, or perhaps you need less than that. Anyway, and if you look at the entries, the 1-1 entry of this, you find this condition, which is only concerns the first row. So I've got a lemma there that says if you give me 5 numbers, 5 complex numbers, so that these 3 satisfy the column 3 condition, and these 3 satisfy the row 1 condition, and if you give me a complex number of modulus 1, I can fill that in uniquely to get an element of U21. Now, you geometry people probably understand where this comes from. I guess it's U21 acts transitively on the ball, and this is somehow a refinement of that. It's just an elementary calculation for me anyway. Okay, so
in fact, that's just a column 1 condition for the inverse.
Yeah.
Which would be a slightly slicker way.
Right, I see. This is a column 1 for the inverse.
For the inverse.
Okay.
G.
Okay. anyway. Is this a little fact here, a familiar fact to? Yeah. Okay, good.
Use it all the time.
Use it all the time?
Yeah.
Really? Okay. Okay, so analogously, we're actually working with matrices which are algebraic integers in this particular field, satisfying this, so f instead of f0. But there are still there are two conditions which are analogs. This is a column 3 condition. This is a column 1 condition, and it's the same calculation tells you that if you give me five numbers in the field, in the cyclotomic field, which satisfy these two conditions, and if you give me a theta in the field of modulus 1, then I can fill in the matrix and get a not only is there a unique G in 3 by 3, but I forgot to say satisfying G star F equals F. I mean, that's the whole point. Okay, so there's a little bit of an omission in this lemma. Okay. Okay, so this provides a nifty method of getting elements of our group, you see, because it factorizes a problem. You first find triple satisfying the column 3 condition, and then for each one you know what the this element here is. You look for a triple satisfying the column 3 condition, and then for each such solution you look for the triple satisfying the row 1 condition, and then you plug in, you make one of the 12 choices of theta, and you will get an element satisfying this. Now we're after elements which have algebraic integers as entries, so the entries might actually just be in here, but it's something easily checked whether they're integral or not. Okay. So to break this down even further, here's a tiny bit of very elementary number theory. I suppose it's about, so we're looking at algebraic integers in this field, and if you take the absolute value squared, it has to be an integer plus an integer times r. And p is positive definite, and q is bounded by 1 over r times p. And not only is it positive definite, but it satisfies that. This is something so easy that I can actually give a proof which might be comprehensible. So if you start with an algebraic integer, its absolute value, its conjugate is an algebraic integer 2, so this is an algebraic integer. It's in K, and so the algebraic integers in K look like this. So we know that you must have an equation like this. Now, there's an automorphism of the field L which interchanges r and minus r and commutes with conjugation. So if you apply it to both sides of this equation here, you get this equation. So if you add the two equations and divide by 2, you find that p is this and q is this. And so that tells you that shows that p is positive always. And this one, you're taking something away from here, which is smaller than this, and so you get this inequality. For this one, I calculated the eigenvalues of a matrix and found the smallest one was a half. So, okay, so that's, so how do we use that? So if you look at the column 3 condition, I wrote it down before, but it looks like this. It's absolute value squared of one algebraic integer, absolute value squared of another algebraic integer, times r minus 1, absolute value squared of a third algebraic integer. And what I do is I write each of these according to the previous lemma. So alpha absolute squared is p plus qr, and so on. So if you plug that into this and the two other formulas into this and equate coefficients of r, you get these two conditions here. So p, which is here, so the right-hand side here, is equal to this. And then you know that the q's are all less than 1 over r times the p's. So this sum is less than this sum. But this sum occurs in the first equation. So you plug that in here. And you get, when I divide by r squared is 3, remember? So when I divide by r, this 3 goes away, so I get a q, and you get this. So this we got from this was in the lemma, and this was what we just worked out. The consequence of that, by the way, is that this q of gamma is the integer part of and so it's non-negative. That follows from this. Okay, so how do we use that? We're looking for elements which don't move the origin very far. So suppose we're looking for g's for which this distance is bounded by a bound b. So that means when you take cosh squared of both sides, you get that the absolute value squared of g3 is at most cosh squared of b. But absolute value is what is the gamma here. The g3 is the gamma here. So this is so this thing here is the absolute value squared of g3, and so 2 times this. So this inequality comes from using one of them here, and the other one from here. But this is g absolute squared. Okay, so you get this inequality here. This 2 at the end is just because this quotient is at most 2. And remember that the p, if you had an alpha which is then the p of it is at most a half of the sum of these. Well, you don't need absolute values, they're just integers. And so 2 times p is at most the sum of, is at least the sum of the squares. Okay.
Sorry, so p is some constant to be
chosen later, yeah. Okay, so if g moves the origin at most b, and its 3 entry is written like this, then you can say that the sum of the squares of the coefficients is bounded by twice the g3 and at most this. Okay. So this is a bit dry, but you see this gives you a very fast algorithm for calculating elements, because the sum of the squares of these coefficients is bounded. All the coefficients are bounded by this particular quantity, and so for moderate b, it's very quick to write down all the possibilities for the 5 elements in the matrix that satisfy the column 1 and column 2 conditions. For each of them, you plug in the 12 possible determinants and work out when these elements here are actually integral. Okay, that's what I'm saying here. So this goes very fast. So So in the other groups we calculated, searching for elements of the group was maybe an overnight job in the simplest cases and a month-long job in others. This one, once you've written the code, you find these elements in microseconds. So in this particular case, you find that the possible distances, by the way, how am I going for time? We're in a state of confusion here, so when did I start? When did I start?
I think you can have more, 10 minutes.
10 minutes or so? Yeah.
50.
Okay. Okay, so the cosh-squareds of the distances are these quantities. Okay, so these are algebraic integers. So their squares look like integer plus integer times r. And if you look, you can see what the first few are. And if you look at our matrix B, its 3 entry is that particular thing. If you take the absolute value squared of that, you find that it's 2 plus r. So that's indeed the smallest distance. So B moves the origin as small as possible amongst the elements which move the origin, actually move the origin. Okay, that's this. So the elements that move the origin that far form a double coset. There's only one double coset which does that. I mean, B is not its own inverse, but it's but nevertheless this double coset is all you need for that. And the next distance with the 4 plus 2r is that particular element there. Is the double coset of that particular element there. Okay. So so for the first few n, I can certainly calculate using this algorithm. I can calculate all of the elements which move the distance at most, which move the origin at most, whatever we want. So this set can be calculated quite concretely for, n equal up to 100 if I like, but but all I need is 2 or 3. Okay. So these sets, of course, they get bigger and bigger, and their union is the whole group. Corresponding to these finite sets, there's a sort of Dirichlet fundamental domain. And sorry, I'm seeing a funny thing there. Is that supposed to be f sub 1? Is that a? Met the mouse. Okay. Oh yeah. Okay. Okay. So these fundamental domains get smaller, and if you take the intersection, you get the Dirichlet fundamental domain of the whole of the group. And you can write down these numbers Rn, which you hope are finite. And this is, Tim will be showing you tomorrow or the next day or something, not tomorrow, but Thursday or Friday, I hope, how you show these things are, in general, how you show these things are finite. So I'm running out of time, so I'm just going to skip any proofs here, but these are elementary proofs. If you happen to know that if you've gone out far enough so that dn is at least Rn, remember, is the radius of this fundamental domain. Dn is the distance you're going out, how far you've moved the origin. If dn is at least Rn, then Sn generates the whole group. If you go out so the dn is at least twice Rn, you actually don't have to go any further. The fundamental domain of the finite set Sn actually is the fundamental domain of the whole group, and everything stops. And you get a set of generators. You get a presentation for the whole group gamma by looking at the elements, the relations that form G1, G2, G3 is 1, where G1, G2, and G3 are Sn. So this is the theorem of Macbeth. in this particular case, in this particular case, you can actually calculate. So there are one or two cases when we can actually calculate these radii precisely. In all the other cases, Tim has a wonderful program which calculates them to a large number of decimal places, which is more than enough. And anyway, it turns out that you can calculate this, these radii precisely in these two cases. So it turns out that you need only n equals 2. So this set S2, which is the sum of the union of these three double cosets, generates a whole group. And the relations G1, G2, G3 equals 1 coming from that S2 give you a presentation. So that's a sketch of the proof of that theorem. So what I wrote down was a cleaned up version of what Macbeth's theorem tells you. Okay. And by the way, thank you to John Parker for he removed one of these pesky relations. Of course, Magma gives you a list, and I suppose Julian, when you've got 3 generators and 35 relations, it's hard work. But sometimes you can remove some of these 35, if you fiddle around enough. And anyway.
I shouldn't have asked you about them yesterday. I was saying we still needed to do some cleaning up.
Right. So anyway, I saw John a few years ago, and he showed me how to get rid of one of the things. So anyway. So then, so now we have a presentation for gamma bar. So we're looking now for torsion-free subgroups of gamma bar of index 864 with finite abelianization. So Magma has got a wonderful suite of algorithms for working with finitely presented groups, and it's got one called low index subgroups. And unfortunately, if you plug in 864, it's just a bit too big. Up to about 50, I've succeeded with other examples, but 864 is just way. You can set it running, and it doesn't blow up immediately, but it doesn't finish. So.
Have you tried that recently? Have you tried that recently?
No.
I
believe it's
not working.
I expect it doesn't. It still doesn't work. I mean, these things are gigantic. So we wrote a specialized C program to do that, and so as I stated before, we found up to conjugacy just one torsion-free subgroup of index 864, but it turned out that its abelianization wasn't finite. So the upshot is that there's no fake projective plane coming from this situation. All right, so is that a good place to stop, or I could talk? Yeah, okay.
I mean, you can have about 3 minutes if you want. But you can stop.
Well, if I've got 3 minutes, why don't I use them? The idea behind the C program is the following very simple idea, that if you do have a torsion-free subgroup, the group acts on the coset space, and any element of finite order has no fixed points. Okay, it's sort of obvious. If this happens, then you would have an element of finite order in pi. So that simple idea, which is certainly implicit in Prasad's paper, is used. And here's a lemma which takes a whole board to write down, and the proof is just 1 line long. If you can cook up an action of gamma bar on a set in such a way that the elements of finite order have no fixed points, then just picking one of the points of the set, you get a torsion-free subgroup. You get a subgroup of which is of the correct index. A torsion-free subgroup of the correct index. So this is an elementary thing too. As I said, it takes more words to write the statement than to prove. But so the idea of the C program that when looking for this is to you take a transversal of our group gamma bar. Because of the first lemma on the second but last slide, we know that transversal can be chosen of this form. We know we can arrange that the action of an element of K is just the obvious one, and so all it is a matter of doing is finding what the action of B of the element little b is. So B has to be a permutation of this set of size 864, and it's got to have all these properties here, and so. We wrote a backtrack. We wrote, for several of our groups, we had to write backtrack searches for things like this. And this one, came to actually finished. So I'm sure deep down inside Magma, it's doing backtrack searches as well. But because of the very specific setup, we can go faster than Magma can in this particular setup. And so you run through all the permutations of 864, which you might think is impossible, but in fact, the fact that, for example, B cubed is the identity and has no fixed points means that its cycle type is consists of 288 triples and so on. So it's actually possible, and when you go looking, a B with the correct property pops out within a day, let's say, of the search starting. One popped out, and my programming skills are not that great, so probably you could finish it all in a week. But I took a few months with multiple computers to run through the possibilities. But I'm sure it can be done better. Okay, I'll stop there.